On our previous lesson, we have learned electric flux. Electric flux. I'll remind that electric flux is equal to surface integral of electric field intensity. Electric field intensity and on square of surface on surface area S. Okay, and let's try to calculate electric flux for positive point charge Q that is surrounded by a closed spherical surface. I'll try to draw this. Surface. Let's imagine such surface. So closed sphere with positive point charge Q in the center of it, in the center of this sphere. Radius of this sphere is equal to R. Radius is equal to R. And let's try to calculate electric flux. Let's try to calculate electric flux for this surface. We can write that it will be equal to surface integral, but to calculate this, it is necessary first of all to simplify integrand. How to do this? If charge is positive, we can notice that electric field intensity can be drawn on the picture in this way. And the element of surface, can be drawn in this way. This is the element of surface, ds. And the element of surface is always perpendicular to this surface. Always perpendicular. So this is right angle between vector ds and surface. And this means that vectors E and vector ds, vector E and vector ds, vector of electric field intensity and vector of element of surface area, they have the same direction, and it means that scalar product or dot product dot product of vectors E and ds, they equal it equal to absolute value of vector of electric field intensity multiplied by absolute value of element of surface area multiplied by cosine 0. Why 0? 0 because vectors have the same direction. If vectors have the same direction, the angle between them is equal to 0. And cosine of 0 is equal to 1. So this will be absolute value of vector of electric field intensity and absolute value of element of surface area. So from here we have that it can be written as it can be written in this way. It can be written in this way. And this integral is much more simpler than this one because now it doesn't contain any vectors, so it is much more simpler than it was before. And how to calculate it? First of all, we have to notice that absolute value of electric field intensity for point charge is equal to 1 divided by 4p epsilon 0. It is from our previous lecture. 1 divided by 4p epsilon 0, charge q divided by r to the power of 2. And this value will be the same for every point of sphere. This value will be the same. In any point of sphere, and it means that electric field intensity doesn't depend on element ds, and it means that electric field intensity may be written outside of the surface integral, ds. Outside of the surface integral ds. And from here we have that this integral contains only elements of surface, so it is equal to area of this surface. So it will be electric field intensity multiplied by area of sphere. But area of sphere with radius r is always equal to 4p r to the power of 2. 4pr to the power of 2. 4pr to the power of 2. And from here we have that so, we can use this and this here. From here we have that it will be it will be 1 divided by 4p epsilon 0 q divided by r to the power of 2 and multiplied by 4 e r to the power of 2. And after simplifying, we get that it is charge q divided by epsilon 0. Divided by epsilon 0. Divided by epsilon 0. And what do we have? We have partial case of general theorem that is known as Gauss flux theorem. Gauss flux theorem in integral form. Gauss flux theorem for electric field intensity. Integral form of Gauss flux theorem. And it can be written for any charge and for any surface. So not only for point charge and not only for a spherical surface. The result will be the same for any charge, and for any surface, So we have, but we don't have enough time to prove this general case, to prove this theorem. But we have learned a simple partial case of this theorem. Partial case point charge inside inside sphere. Point charge inside sphere. So integral form of Gauss flux theorem. Gauss flux theorem or Gauss law. There is also another name, or Gauss law for electric field intensity. For electric field intensity. For electric field intensity. Integral form, and it can be written. It can be written for every closed surface. For every closed surface, we have that electric flux is equal to charge inside the closed surface. QS means charge inside the closed surface. And for charge that is outside of the closed surface, electric flux will be equal to 0, according to this theorem, according to this Gauss law. For charge outside, and for charge inside, for charge inside, electric flux will be equal to this. Will be equal to this, and it can be also written and can be also written using triple integral of electric charge density. Vs means volume inside closed surface, S, and here we have rho q, rho with lower index q, and it means that electric charge density inside closed surface, and multiplied by differential of volume. This is integral form of Gauss flux theorem for electric field intensity. Okay, so do you have any questions about this? Do you have any questions? No questions. No questions. Okay, if there are no questions, I will clean this. I'll remove this, and I will leave just this formula in red frame, because we will need this for our further learning. And if we have integral form, we can make a suggestion that we also may have differential form, and we have this. Maybe you can remember from calculus. There are Gauss-Ostrogradsky theorem in calculus. In calculus, we have a theorem. Yeah, but here I will draw also this round. Round means that we have a closed surface. That F is closed surface. This integral, double integral with round, means that we have surface integral on closed surface, and according to calculus, this integral is always equal to triple integral from integral on volume Vs, volume inside closed surface, and here we have div E. It is from your calculus course. Now I will remind what does it mean. Div E. What is div E? Div E is divergence. It is divergence. And this is equal to operator, equal to Hamilton operator dot product function E, and this will be if we write this in extended form, if we write this in extended form, we will have that it will be dx I plus plus d plus d dy yod and plus d d z k d dz k dz k and multiplied by e and this is equal to this is equal to dE according to the properties of scalar product d dx plus d e y dy and plus d e z d z and so this div operator is known as divergence. This divergence um, divergence it is from calculus or mathematic analysis. It is from calculus or mathematic analysis. Okay, and if we use this theorem, so from here and from here and here, we have that divergence of electric field intensity is always equal to electric charge density divided by electric constant. Okay, so do you have any questions about this? Do you have any questions? No questions. Okay, if there are no questions, we can write that differential form. Differential form of Gauss flux theorem or Gauss law for electric field intensity. For electric field intensity. For electric field intensity. Differential form. And This differential form can be written in this way. It is useful when we have electric field intensity as a function of coordinates. Using this theorem allows us to find density of electric charge. Allows us to find density of electric charge. Okay, and let's remember that electric field intensity is for electrostatic field is always equal to minus gradient of electrostatic potential. Always equal to minus gradient of electrostatic potential. So from here we have that divergence E will be equal to minus according to this and this and this. It will be equal to gradient multiplied by gradient phi electrostatic potential, and this is the same as gradient operator to the power of 2, and this is the same as minus how to write this, I will copy this here. And phi, and according to the properties of scalar product, and according to properties of E yod k ors, we have that E is perpendicular to yod, and this is perpendicular to k in Cartesian coordinates. And this means that for example, E multiplied by E is equal to absolute value of E, and this is equal to 1. And for example, E multiplied by yod is equal to modulus of E, modulus of yod, multiplied by cosine of 90 degrees, and this will be 0. And the same situation with the other course. So from here we have that it will be minus and I'll make some changes. Here we have to the power of 2. To the power of 2. Here we have and multiplied by phi. Multiplied by phi. So we have obtained that divergence E a divergence of electric field intensity is equal to minus Laplace operator of phi, and this is now I will explain this. It is from here. From here we have that Laplace phi is equal to this to the gradient operator to the power of 2 phi, and this will be here. And of course it is equal to this. I will just change some phi and phi. This is Laplace operator. It is Laplace operator. Laplace operator. It can be written as a simple triangle. So this is Laplace operator. Laplace operator. This is Laplace operator. And using this Laplace operator, we have obtained from here and here that from this and this we have that Laplace operator of phi is equal to minus electric charge density divided by electric constant. And this equation this equation is known as Poisson equation. So we have obtained Poisson equation. Poisson equation. Poisson's equation. Sorry, I have some trouble with my internet connection. I have some trouble with my internet connection, but it is not very bad. Not very bad. We will. I hope we will remember what we have learned. You will remember what we have learned. So we have learned a few things. The first thing is integral form of Gauss flux theorem, or Gauss flux law, for electric field intensity. Field intensity for electric field intensity, and according to this, we have that electric flux of electric field intensity through closed surface S is always equal to electric charge inside this closed surface, and epsilon zero, and this is always to 1 divided by epsilon zero triple integral of electric charge density by volume. And we also have written differential form. Of this Gauss flux law. Differential form. So integral form is here. Integral form is here, and this is integral form, and differential form is divergence E, is equal to rho u, density of electric charge, divided by epsilon 0. Divided by epsilon 0. Divided by epsilon 0. And and what is divergence? Divergence is a vector differential operator that can be written in the next way. The next way, div E is equal to gradient operator multiplied by E scalar product. This is scalar product, and this will be d by dx E plus d by dy j and plus d z k E vector, and this will be equal to d e x by dx plus d e y by dy and plus d e z by d z by dz. So this is divergence. This is divergence operator, and we have also learned Laplace operator. Laplace operator. Laplace operator. And what is Laplace operator? For example, Laplace operator of scalar function phi means gradient operator to the power of 2 of this and this is the same as by dx to the power of 2 plus d2 by dy to the power of 2 and plus d2 by dz to the power of 2 phi. And this is the same as dx to the power of 2 plus I'll just copy this voice and change and make some changes. This is Laplace operator. Here we have y and z. Y and z. This is Laplace operator. Laplace operator. And this and we have proved Poisson's equations. Poisson's equation, and according to this equation, Laplace operator of electrostatic potential is always equal to minus minus electric charge density divided by electric constant. Divided by electric constant. Divided by electric constant. Okay, do you have any questions? Do you have any questions? So we have learned some things about electrostatic field in vacuum. Okay, and now let's have a look. Let's have a look at electrostatic field in some media. What does it mean? It means that we are learning electrostatic field in some substance. So we have atoms, ions, and molecular. And as you know, atoms, ions, molecular are consist of electrons and protons. So they contain positive and negative charges. They contain positive and negative charges. And these charges cannot move, they cannot leave their places without additional energy. They cannot leave their places. And because of this fact, they called bound charges. And before this, we have learned charges that can move, and charges that can move without much additional energy. Charges that can move without much additional energy are free charges. And charges that cannot move without additional energy are bound charges. And in media or substance, usually number of positive and negative bound charges, numbers of positive and negative bound charges are equal. And we can consider a so-called electric moment. Electric moment. What is electric moment? It is a vector that can be written for a pair of point charges. Electric moment is equal to Q I multiplied by L I vector. And what is Qi and Li? I will try to draw a picture. I will try to draw a picture. In this picture, no, it is necessary to write an arrow. In this picture, we have that this is vector Li. This is vector Li. And this is charge minus Qi. And this is charge plus Qi. Minus Qi and plus Qi. Plus Qi. So vector Li is directed from negative to positive charge. From negative to positive charge. And for 2-point charges, that have the same absolute value, but one of them is positive and one of them is negative, we may use electric moment. We may use electric moment for pair of charge, for pair of point charges, And for some dielectric media, dielectric is media that contains mostly bound charges. Dielectric contains a very small number of free charges, and the most of charges in dielectric are bound charges. Bound charges, they cannot be easily moved from their places in dielectric. So in the situation of absence of internal electrostatic field, electric moments in dielectric will be oriented chaotically. And it means that in case of absence of internal field, we will have that sum of these electric moments in dielectric will be equal to 0, because they are oriented in different ways. They are oriented chaotically. And what will we have if we put dielectric into internal field? For example, I will show this field in this way. For example, we have external field. We have electrostatic field in dielectric, and if we have this field with electric field intensity, we may see that there will occur some electrostatic forces. Here will occur electrostatic forces that acts in this way. We will have some electrostatic forces. In this case, some electrostatic forces that try to orient electric moment in this way. So electrostatic forces in external electrostatic field try to orient electric moment in direction of electrostatic field. And it means that it means that this sum will not be equal to 0, in presence of external electrostatic field. So in presence of external electrostatic field, we will have that this sum is not equal to 0, and this fact allows us to define new physical value that is known as polarization density. Polarization density. Polarization density. Polarization density. Polarization density. And what is this? Polarization density is vector P that is equal to sum of electric moments of bound charges divided by some volume. So in numerator we have sum of electric moments in volume delta V, and in denominator we have this volume. So this is a vector of polarization density. Okay, and do you have any questions about this? No questions. Okay, and the next question is I have typo here. It is necessary to polarization density. And okay, red frame. And the next question is what is the connection between electric field intensity and polarization density? In simplest case of the electric, in the simplest case, we have simple connection. That P is equal to kappa epsilon 0 E vector. This is simplest case. This is the simplest case of the electric, and we will learn only this simplest case. We will not learn more difficult cases because we don't have enough time, and we don't need this. Because these are very difficult specific things. Where kappa is a property of substance or media, and this is known as electric susceptibility. Electric susceptibility. Electric susceptibility. Electric susceptibility. This is electric susceptibility. So in the simplest case, we have this this simple connection between polarization density and electric field intensity. Okay, so do you have any questions about this? Do you have any questions? No questions. No questions. Okay, and if we have polarization, we will obtain redistribution of bound charges inside the electric. What does it mean? It means that in one part of the electric, there will be more positive bound charges, and in the other part of the electric, there will be more negative bound charges. And how to calculate these bound charges? How to calculate these bound charges in the volume of the electric? In this case, we have similar theorem. We have Gauss flux theorem, Gauss flux law for polarization density. We have Gauss flux law for polarization density. And how to write this? Gauss flux theorem. Integral form. Integral form of Gauss flux law or Gauss flux theorem for polarization density. And we have integral, and we also have differential form. Differential form also have differential form. So integral form f p flux of polarization vector. According to the definition, it is equal to surface integral closed surface p ds and this will be equal to q minus q. This is bound charge inside closed surface, inside any closed surface, and this will be this will be equal to triple integral. This will be equal to triple integral of but with minus, of course, with minus triple integral of rho u dv, rho q and dv. So this is integral form of Gauss flux law, and we can also use we can also write differential form, and according to this differential form is divergence of vector p is equal to minus density of bound charges, minus density of bound charges, minus density of bound charges, minus density of bound charges. Okay, do you have any questions about this? Okay, if there are no questions, let's have a look at some surface between two dielectrics, or between dielectric and vacuum, or between dielectric and vacuum. So let's have a look at some surface. This is a surface, and here we have the surface on boundary between two dielectrics. In the first dielectric, we have polarization density P1, and in second dielectric we have polarization density P2. P1, P2, P1 and P2. Okay, and the element of this surface, is some ds, and it is always perpendicular to this surface. So here ds, this is ds, and we can also define some normal vector of normality to the surface, vector of normality to the surface, and here we have this vector n. So we have that modulus of absolute value of n. Absolute value of n is equal to 1, and vector n is has the same direction as vector ds. So n is unit vector that is perpendicular to the surface. Okay, and let's use integral form of Gauss flux law for this for bound charge on this surface. For bound charge on this surface. So for element ds, according to this theorem, for element ds, for one element ds, we have that d dq bound charge is equal to minus p ds. But we have two vectors, so we have to write p2 ds minus p1 ds. Okay, and let's write this using vector n. Let's wait. We can open brackets. It will be p1 ds minus p2 ds minus p2 multiplied by ds. And this will be if we use this, we can write ds as vector n multiplied by absolute value of ds. So we have p1 multiplied by n minus p2 multiplied by n ds. No, without vector, because we use that if we have this from here, we can write that it will be ds multiplied by n vector, because absolute value of vector n is equal to 1, and it has the same direction as vector ds, and because of these two facts we can write that it will be ds multiplied by n. Okay, and p multiplied by unit vector n, it can be written as a projection of vector p on the direction that is perpendicular to surface. So it will be p 1 n minus p 2 n multiplied by ds. Yes. Okay, and do you have any questions? No questions. No questions. Okay, if there are no questions, I will clean some unnecessary things. I'll clean some unnecessary things and from here we have that bound charge on surface, on boundary between two dielectrics, or on boundary between dielectric and vacuum. From here we have that surface density of electric charges is equal to surface density of electric charges. This will be P1n minus P second n minus P second n. And what is the sigma with this sign above this? It is surface density of bound charges. Surface density of bound charge. So this is dq divided by ds. And this is surface density. Surface density of bound charge. 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 Okay, and do you have any questions about this? Do you have any questions? So we have on boundary between on boundary between or on surface boundary between maybe it is best to write border. On border between two dielectrics or border between dielectric and vacuum. Trick and vacuum. Dielectric and vacuum. Border between dielectric and vacuum. So in this case we have such formula for surface density of bound charge on this border. This border. Okay, and do you have any questions about this? No questions. Okay, so let's have a look at Gauss flux theorem. Gauss flux theorem. This Gauss flux theorem. In case that we have, when we have both free and bound charges. In this case, we can write Gauss flux theorem. We have that it will be E ds EDS, and this is equal to free charges inside surface S, free charges plus bound charges, plus bound charge, divided by epsilon 0, divided by epsilon 0. And from here we have surface integral epsilon 0. Epsilon 0 is electric constant, so integral and constant may be changed. Places of integral and constant may be changed. So it is surface integral, and the integral function is epsilon 0 e, and this will be equal to qs, free charge inside closed surface S, plus bound charge inside this closed surface. Okay, and but for charge, for bound charge inside closed surface, we also have Gauss flux theorem. We also have Gauss flux theorem for bound charge. We have this Gauss flux theorem for polarization density, and it contains bound charge inside a closed surface. And according to this, we have minus surface integral S P ds. Okay, and from here we obtain that surface integral of epsilon 0 e plus p and ds, and this is equal to free charge, only free charge inside closed surface S, free charge inside closed surface S. And this value in brackets is known as electric displacement vector or electric induction vector. Electric displacement vector. Electric displacement vector or electric induction vector. Or electric induction vector. Or electric induction vector. And this is D, and this is equal to epsilon 0 e plus p, And as you can remember, vector P, vector of polarization density, can be calculated as kappa epsilon 0 E. So we have that P is equal to kappa epsilon 0 E, electric field intensity. And from here we have that epsilon 0 E plus kappa epsilon 0 E. And this is equal to 1 plus kappa epsilon 0 E. And this is equal to epsilon 0 E. So epsilon 0 E. Epsilon 0 E. Epsilon 0 E. And this epsilon that is equal to 1 plus electric susceptibility, 1 plus kappa. This is relative permittivity. Relative permittivity is relative permittivity. This is relative permittivity. Finally, we have that. Displacement vector, electric displacement vector is equal to epsilon 0 E plus P, and it is equal to epsilon 0 E, where E is electric field intensity and epsilon is relative permittivity. And from here we have integral form of Gauss flux theorem or Gauss flux law for electric displacement vector. Electric displacement vector or electric induction vector. Induction vector or electric induction vector or electric induction vector. And we will also have differential form. So I will differential form. So for integral form we have F flux of displacement vector is equal to surface integral S d ds, and this is equal to qs free charge inside the closed surface S, and this is equal to triple integral vs rho q dv rho q dv. Rho q dv, and differential form will be divergence divergence d is equal to rho q differential form. Okay, and the last for today is what about vacuum? In vacuum there are no bound charges. In vacuum there are no bound charge. There are no any bound charge in vacuum, so there is no polarization. There is no polarization in vacuum. We have P is equal to 0. Then D is equal to epsilon 0 E. D is equal to epsilon 0 E. D is equal to epsilon 0 E, and from here we have, if D is equal to epsilon 0 E, we have for vacuum that epsilon is equal to 1, and relative permittivity and electric susceptibility is equal to 0 in vacuum. So in vacuum we have this. Okay, do you have any questions? Okay, so if there are no questions, thank you for your attention, and I hope to meet you tomorrow. Tomorrow when we will do some practical exercises. Okay, thank you. Have a good day.